Let's talk about variation of parameters. It's to find a particular solution of a second order linear non-homogeneous DE where these coefficients can be functions of x. And you already know a fundamental set of solutions, say y1 and y2, to that homogeneous. So y1 and y2 are solutions of this homogeneous that are also linearly independent. So the idea or the approach for this is going to be slightly different than we've done before. But y1 and y2 are again solutions to that homogeneous, and so instead of just having one of these functions, we're going to have a combination of both of them as the guess for what our particular looks like, where u1 is some function of x and u2 is some also function of x that we have to go and find. The beauty behind this is, well, we know it's going to be a solution to that non-homogeneous DE, so well, we need a second equation because we have two functions, two unknowns that we need to find, which means we are allowed to give ourselves another restriction, so to speak. So without going into the details now, I'll go into the details in class, but what that means is you can have this restriction right here, which zeroes things out nicely to make your life a little easier, and this one. So to find u1 and u2, we're going to solve the following system to figure out what essentially u1 prime and u2 prime are, and then we'll integrate to get u1 and u2, which will then plug back into the particular solution, which will then have our particular solution that we were looking for. So let's try an example. So we would like to solve this second order linear non-homogeneous DE, x squared y double prime minus 4xy prime plus 6y equals x to the 5 halves. Given that we already know y1 x squared and y2 equals x cubed is a solution, both of them are solutions to the homogeneous. So what that means is my homogeneous solution is going to look like c1 x squared plus c2 x cubed. So I have to go find my particular, which is going to look like some u1 times y1, which y1 is x squared, plus u2 times y2, and my y2 is x cubed. To figure out what that u1 and the u2 are, I'm going to plug them into that system, which again looks like u1 prime y1 plus u2 prime y2 is equal to 0, and u1 prime y1 prime plus u2 prime y2 prime is equal to f of x divided by p naught of x. So u1 prime, I don't know. y1 is x squared plus u2 prime, I don't know, times y2, which is x cubed, should be equal to 0. Second equation, u1 prime times y1 prime, which will be 2x, plus u2 prime times y2 prime, which will be a 3x squared, should be equal to f of x, which for this question is x to the 5 halves, divided by p naught of x, and p naught of x is always that coefficient on y double prime, so x squared in this case. Which, that simplifies to x to the 5 halves over x squared, simplifies to x to the 1 half. So now I have to solve this system right here. And the way I'm going to do this is I'm going to take this first equation, and I'm going to solve for u1 prime. So u1 prime is equal to negative u2 prime x cubed divided by x squared, which looks like a negative u2 prime times x. I'm going to take that in. This is u1 prime. I'm going to plug that in here into the second equation for u1 prime. So 2 times negative u2 prime x times x plus 3 u2 prime x squared is equal to x to the 1 half. So now I have an equation which is u2 prime, so I can also find u2 prime. So u2 prime times the entire quantity, negative 2x squared plus 3x squared, which is just u2 prime times x squared, should be equal to x to the 1 half, which gives us u2 prime is x to the 1 half divided by x squared, which simplifies to x to the negative 3 halves. So now I know this is u2 prime which means I can take this and plug it back in here to tell me what u1 prime is. So u1 prime is equal to negative u2 prime, which is x to the negative 3/2, times x, which that just simplifies to x, negative x to the negative 1/2. So now I have u1 prime and u2 prime, which means I can integrate them to find u1 and u2. So u1 will be the integral of negative x to the negative 1/2 dx, which gives me a x to the 1/2 negative 2. I'm going to pick my constant of integration is equal to 0 because I'm just looking for a particular solution, and then my u2 is equal to the integral of x to the negative 3/2 dx. Which gives me x to the negative 1/2 divided by negative 1/2, which gives me a negative 2x to the negative 1/2. Okay, so as a reminder, my particular solution was going to look like u1 x squared plus u2 x cubed. Well, now I know my u1 and my u2, so my particular solution looks like u1 negative 2x to the 1/2 times x squared plus u2, which was a minus 2x to the negative 1/2 times x cubed, which gives me negative 2x to the 5/2 minus 2x to the 5/2, which is a negative 4x to the 5/2. So again, this was my particular solution. I already had my homogeneous, which as a reminder, that was the homogeneous solution was c1 x squared plus c2 x cubed. So it means my overall solution to that dE, y, is always equal to the homogeneous plus the particular. So in this case, it's a c1 x squared plus c2 x cubed plus the particular, which is a minus 4x to the 5/2. So there's my solution to that dE, where again, I already knew what the solutions to the homogeneous were. I didn't cover how to find those at all. Variation of parameters. This approach is just to find a particular solution when you already have that fundamental set of solutions.